Let us continue today with our discussion of vectors. Specifically, we start with vectors in a plane, and I would like to talk about a few subjects today, a few topics which would include, for instance, the idea of scalars and pseudoscalars. I will elaborate on that, and then we will look again at plane polar coordinates, discuss unit vectors, and finally the target is to try and understand kinematics in a plane in terms of plane polar coordinates, because it is of great practical importance. So let me start by pointing out that we defined a vector as a set of quantities, the same number of quantities as the dimensions of the space that you are interested in, which transform under rotations of the coordinate axis in exactly the same way as the coordinates themselves transform. So in a plane, we have already seen that if you took a frame of reference, the xy axis like so, and then you took a tilted frame rotated at some angle theta with respect to the first coordinate system y prime, then we had a set of transformation rules which said that the coordinates of an arbitrary point P, if they are x and y in the original frame of reference, then x prime is x cos theta plus y sin theta, and y prime equal to minus x sin theta plus y cos theta. And the next statement, just to repeat what I have said already, is that if you have a vector, any vector u, which has got components u sub x and u sub y, then u is a vector if and only if ux prime and uy prime are related to ux and uy in exactly the same way as x prime and y prime are related to x and y. That is the definition of a vector. Now once we defined a vector in this fashion, we introduced the idea of a dot product. So if you have a vector A which has got components ax and ay, and another vector B which has got components bx and by, then from these two quantities, from these two vectors A and B, you can actually form three different scalars. One of them is a squared, which is ax squared plus ay squared, and similarly bx squared plus by squared. And the third scalar that you can form, quantity which does not change under rotations, the third scalar is a dot b, which is equal to ax bx plus ay by. That too is a scalar, and that is why we call this the scalar product, the dot product, or the scalar product, more correctly the scalar product. Now what this implies is that this particular combination of A and B, this rule of multiplication, tells you how to take two vectors and get a scalar out of them, create a scalar out of them. And it is clear that this is just the same as A dotted with itself, and this is the same as B dotted with itself. So this is A dot A by definition, and similarly for B. So the dot product or the scalar product is a way of creating a scalar from a vector, and so far we have restricted ourselves to a plane, to two-dimensional vectors. I also pointed out something else. I also pointed out that interestingly, if you consider the combination ax by minus ay bx, that too appears to be a scalar, and this needs a little bit of working out, and it is not a very hard thing to do. So let me do that and show you how this happens. So if you looked at ax by primed minus ay prime bx prime, substitute for ax and bx and ay and by formulas similar to this. So you have a little bit of algebra to do. You would have to write ax prime is ax cos theta plus ay sin theta, and similarly for b x prime and by prime. Put that all inside this and do the simplification, and it is a simple exercise to show that this will turn out to be equal to ax by minus ay bx. So just as this quantity was equal to ax prime bx prime plus ay prime by prime, In exactly the same way, this combination, this antisymmetric combination also remains unchanged under rotations, and therefore we would call it a scalar. But it is really slightly different, a slightly different kind of scalar than the scalar we have been talking about, because so far we restricted ourselves to pure rotations. But you can also ask what happens if, for instance, I go from a right-handed coordinate system to a left-handed coordinate system. For instance, suppose I reflected about the y-axis and the new coordinates were in the following fashion, will look like this. You had y prime and x prime here in this direction, or for that matter you reflected about the x-axis and you had y prime and x prime over here. These coordinate systems cannot be obtained from the original xy coordinate system by rotating about the origin. No rotation about the origin, about any angle, will ever produce this coordinate system from this. Because if you start rotating this like so to bring the x-axis to point in this direction, the y-axis will point downwards. But that is not what is happening here, nor is it happening there. So these transformations I mentioned briefly last time were improper transformations. So we have to worry about what happens to vectors under improper transformations as well. So let us ask, what happens if I have a transformation which say takes you from this coordinate system to that coordinate system? What does that imply? That says x prime is minus x, y prime equal to y, because the y prime axis is exactly the same as the y axis. But the x prime axis is the negative of the x axis, and therefore x prime is minus x. What happens under this transformation? Well, the coordinates transform in this fashion, and therefore any vector would transform in exactly the same manner, which means that this combination that you have here is going to look like this. You are going to have ax prime equal to minus ax by ay prime equal to ay, and similarly bx prime equal to minus bx and by prime equal to by. What happens to this combination here? It is clear that if this thing changes sign, ax prime goes to minus ax and bx prime goes to minus bx. Under such a transformation, this implies that ax prime bx prime plus ay prime by prime is equal to, this changes sign, so the product does not change sign. It remains once again ax bx, and of course the y's do not change sign at all, so ay by. Therefore this quantity is a scalar not only under rotations but also under reflections. Of course if you have a reflection about the x axis, it is a simple matter to see that what will happen then is that the x components do not change sign, the y's do, and exactly the same thing goes through here. So this is a true scalar. Not only under rotations but also under reflections, under improper transformations. But look at what happens to the other combination. Look at the combination ax prime by prime minus ay prime bx prime. This is equal to, well, ax prime changes sign, by prime does not change sign, so you have a minus sign. So this is minus ax by plus ay bx. Because this does not change sign, that changes sign and cancels the minus sign, give you a plus there. But this is equal to minus ax by minus ay bx. So you see this combination, which was a scalar under rotations, has actually changed sign under reflection. So under a proper transformation, and a rotation is called a proper transformation because you can continuously start from the original coordinate system and go to the new coordinate system smoothly whereas a reflection is a sudden transformation, if you like, a discontinuous transformation. Under a proper rotation this remains like a scalar, but under a reflection it changes sign. Such an object is called a pseudoscalar. It is still a scalar under rotations, but its transformation under reflection is different from that of a true scalar. And now this tells you that there are different kinds of scalars that you can possibly have. In this case we have seen two different kinds of scalars. This will also generalize as we go to higher dimensions to vectors. You will have quantities which look like pseudo vectors, and at that stage I will give physical examples of these quantities. Just to cut a long story short, in 3 dimensions the position vector is a true vector, the momentum vector is a true vector, the angular momentum vector for instance will turn out to be a pseudo vector. It will have a different transformation property under reflections or parity than a true vector does, and we will see how. So it makes it makes sense to deal with these to discuss these matters, because physical quantities have specific transformation properties and it is important to understand how and why this happens. Alright, now that we have done this, let us go back a little bit to what we were discussing, namely plane polar coordinates, and I should now like to talk about the unit vectors and what happens to them as the position changes. So let us go on to this topic now, that is over. Let us go back to this and look at what we had said about plane polar coordinates. Here is the x axis, here is the y axis, that is the origin, and my point was that any point P which has coordinates x and y in Cartesian coordinates could also be regarded as having coordinates or plane polar coordinates, and I used a symbol r for this distance and an angle phi, the angle from the x axis to the line joining the point to the origin, and this quantity I called it r. I should now like to change that notation a little bit, because I would like to reserve r for the distance from the origin to a point in even 3 dimensions, and I do not want to confuse that with this r here. So let me call this rho, this distance rho. So you can use rho and phi, and this rho is just x squared plus y squared square root, and this phi is tan inverse y over x, and the corresponding inverse transformations were x equal to rho cos phi and y equal to rho sin phi. I am rewriting these same formulas that we wrote down the last time, except I have replaced the symbol r with the symbol rho, because I do not want to use the symbol r in 2 dimensions. I would like to use rho, because when I go to 3 dimensions then it will turn out that the projection onto the plane, onto the xy plane, that distance I will continue to call it rho for consistency. Okay. Now what are the ranges of these variables? Well, minus infinity to infinity in the case of x and y, that translates here to 0 less than equal to rho less than infinity, and 0 less than equal to phi less than 2 pi, to make it single value. So those were the ranges. These are the transformation formulas from Cartesian to polar coordinates, and these are the transformation formulas from polar coordinates to the Cartesians on this side. Okay. Now any arbitrary point P, such as the one I have written here, could always be written this point, the radius vector to this point is the vector rho. And its magnitude is rho without the arrow. So we immediately have rho equal to rho times E sub rho, where this is the unit vector in the radial direction, in the direction pointing away from the point along the line joining the origin to that point. So this is the unit vector E sub rho. And then this vector rho, this is this distance is rho, this distance is rho, and it's pointing in that direction. So it's clear that the radius vector from the origin to any point is the magnitude rho multiplied by the radially outward unit vector. I'll call this the radial direction. This angle that we have here is phi, is the azimuthal angle. I could of course also write this rho as x times E sub x plus y times E sub y, where Ex and Ey are unit vectors. So this is the unit vector in the x direction Ex, that is the unit vector in the y direction E sub y. And I pointed out that wherever you are in the plane, the unit vectors in the x and y directions remain unchanged. Unlike the radial unit vector, which changes. If I go to this point, it points outward like that. If I go here, it points up this fashion, and so on. And we'd like to know what's the dependence of this E rho on the coordinates themselves. Well, that's easy to write down, because all you have to do is to take this vector E rho and resolve it along Ex and along Ey in this fashion. Of course, by the law of corresponding angles or whatever, this angle is also phi. This direction is the direction of Ex, and that direction is the direction of Ey. Remember, Ex is the same thing as the unit vector I, and Ey is the same thing as the unit vector j. I prefer to use Ex, E sub x, E sub y, etc., because it immediately tells me along which direction it is, and I am going to extend this to higher dimensions as well. Okay. So you have E rho pointing radially outwards, and this is Ex and that is Ey, and the question is, how do I write E rho in terms of Ex and Ey? And it is obvious from this figure that E rho is composed of a vector along this direction and a vector along that direction. The magnitude of this vector here, E sub rho, is unity, and this angle is phi. Therefore, the x component is just cos phi. So this is cos phi times Ex plus, and the vertical component is the sin phi, because this distance divided by 1 is equal to sin phi. So this is sin phi times Ey. That is a basic relationship. It is a basic relationship, and it immediately tells you exactly what I have been saying all along, namely that the unit vector in plane polar coordinates is going to be dependent on the position on the coordinates themselves. In this case, it turns out that E rho is a function of phi. If therefore you go to some other phi in this direction, E rho points like that, and it depends on this angle, it changes. Now you could ask, why does it not depend on rho itself? It does not depend on the magnitude rho. That is immediately clear, because if you are at this point, that is the radial vector, unit vector, but if you are at this point with a larger rho, you are still in the same direction, does not matter. Therefore, it is not surprising that E rho is a function only of phi and not of rho. So if I were to in general write this as a function of this distance and phi, there is no dependence on this quantity. It is a function only of the azimuthal angle, and that is geometrically immediately obvious from this figure. What we need to do now is to ask, after all, if I have an arbitrary point here, this vector, I can resolve this vector along the x direction and along the y direction. Can I do so in polar coordinates? Can I resolve any point, any vector here at this point along the radial direction and normal to the radial direction. What normal shall we choose? Well, we should choose the normal in which, just as originally I choose the direction of Ex to be that of increasing x and increasing y, here I choose it in the direction of increasing rho, and I should choose it the other vector in the direction of increasing phi, the azimuthal angle. But this azimuthal angle is measured from this line in the positive sense, and therefore when you increase it, it should therefore move in this direction here, perpendicular to E sub rho. So if this is E sub rho, the unit vector that is perpendicular to it is E sub phi. Again, it is easy to see what it will look like in Cartesian coordinates in terms of Ex and Ey, because the same figure, Ex along here, Ey along here, this angle is phi, therefore this angle is phi immediately, and E phi has a component along Ey, and this angle is phi. So it is clear that E phi equal to cos phi times Ey, because this angle is phi and the projection of this on that direction has a cosine and it is along Ey. But the projection along the x direction is in the negative Ex direction, and it is this height which is sin phi. So this rest of this formula is minus sin phi times Ex plus E0 cos phi. Again, as before, it is immediately clear that E phi also is a function only of phi, does not have rho dependence in it at all. Okay. It depends on phi, and that is clear too, because if I were at this distance, E phi is along a direction which is tangential to this circle of constant rho, but if I move a little further, it is again tangential to the circle, and these two guys are parallel to each other with no dependence on the distance from the origin. So immediately you see that E phi also depends only on phi, does not have a dependence on rho at all. So now we can go to work. We have a unit vector system Ex Ey, we can use these formulas, or E rho and E phi. When we work in plane polar coordinates, you should use these unit vectors, and in Cartesian coordinates you use these vectors, with the important difference that these two unit vectors will depend on the azimuthal angle. So therefore it will depend on the location of the point in the plane, but they are unit vectors all the same. And just as we know that Ex dot product with Ey equal to 0, because the cosine of the angle between them is cos pi over 2, which is 0, they are at right angles to each other. Similarly, this construction shows that E rho and E phi are perpendicular to each other, but it is a simple matter to verify that E rho dot E phi is the x component times the x component plus the y component times the y component, and therefore this is equal to minus cos phi sin phi plus sin phi cos phi, which is identically equal to 0. So they are indeed at right angles to each other. Okay. And it is equally straightforward to see that E rho dot E rho equal to E phi dot E phi equal to 1. They have to be, it has to be so, because the length of this unit vector is of course 1 by definition, and that follows from the fact that cos squared phi plus sin squared phi is 1 immediately. So we have another orthogonal set of unit vectors to describe vectors in the plane, either Ex and Ey or E rho and E phi, depending on the application, depending on what you would like to do. The next task now is to see whether we can use this to understand motion of a particle, say in a plane, whether we can understand kinematics in a plane, and this requires the following kind of construction. So we have unit vectors. Oh, by the way, an exercise, a small exercise. Write Ex and Ey in terms of E rho and E phi. I already wrote down formulas which expressed E rho and E phi as linear combinations of Ex and Ey, and now what you should do is to write Ex and Ey as linear combinations of E rho and E phi, okay, and verify that Ex and Ey do not involve, they should not involve the coordinates themselves, because they are constant vectors. These are both in magnitude and in direction. Whereas E rho and E phi are unit vectors, magnitude is always 1, but the direction changes from point to point. Alright, now what we would like to do is to understand how a particle moves in a plane, and the reason I have called it kinematics is because we are not going to specify at the moment what the forces on this particle are. So we are not going to talk about its actual motion under some given force, which would be part of dynamics. On the other hand, kinematics is that part of dynamics, that part of the study of motion, which is independent of what the force on the particle is, which is independent of any specific given force or any given initial condition. This is just general formulas which arise essentially from geometry, just the definition of things like the velocity, acceleration, and so on. Now first of all, if you have a particle moving in the plane in some arbitrary trajectory in this fashion, that is the path of a particle as a function of time, say, then what you should do to understand the motion of this particle is to use the fact that its position vector at any particular point is the radius vector, which we call rho in this fashion, and that is a function of time. It changes from time to time. So rho is a function of time. The position vector of a particle in a plane, moving in a plane in some arbitrary fashion, is a function of the time. Okay. Then I would like to see what the velocity is, what the acceleration of this particle is, and so on. Now what does this mean? Well, at a later instant of time, if the position vector is there or here, for example, so that is the position vector at a later instant of time. This is rho at time t, this is rho at some time t prime greater than t, say, particle. Then it differs from rho of t in two possible ways. One is its direction is different in general, and the second is its magnitude is different in general. So therefore when I say the velocity, which is the rate of change of this rho with respect to t, you have to take into account both factors, the fact that its direction may change as a function of time and that its position may change as a function of time. So the velocity of this particle, and let us call this position rho of t, position rho of t, its velocity v of t, and we would also be interested in its acceleration a of t, because dynamics is going to come in when we specify the acceleration of the particle. We are going to say under a given force, we are going to use Newton's laws and say the force is equal to the mass times the acceleration, and then we are going to have to solve for the position in general. So the idea is if you give me the force of the on the particle at any instant of time, you are giving me its acceleration, and the problem in dynamics is to work backwards from that and discover what its velocity is, and then again backwards to discover what its position is as a function of time, so that you can predict the trajectory of this particle. So that is the basic problem of particle dynamics. Now what is this velocity? As you know from calculus, this is equal to the rate of change d over t of rho of t, and that is the definition of the velocity. In the acceleration, by definition, is d over dt of v of t, and that of course is equal to d2 over dt2, the second derivative of the position. So if you like, the problem of dynamics, particle dynamics at this level is to say that if the second derivative with respect to time of the displacement or the position is given to you, can you work backwards and find the first derivative, namely the velocity, and then can you work backwards and find rho of t. These are derivatives, differentials. Therefore, when the inverse problem will involve integration, you have to essentially do two integrations in order to discover this point, and that is called solving a differential equation for this quantity. Right now we are not going to do dynamics, we are going to do kinematics. So all I am going to do is to write down formulas for the acceleration and the velocity given the position and given the fact that this position will change both in distance from the origin as well as the angle, azimuthal angle. So this is the target.